Okay, here's a quick run through of our notes for Unit 6 on chemical reactions. We're going to talk about what they are, how to write and balance them, how to identify their types, and then we're going to experience them in lab today, or during this unit. Okay, so first thing, what are chemical reactions? So a chemical reaction is anytime we reorganize atoms or electrons in some sort of substance through chemical process. We've kind of talked about this earlier in the year too. We have to break and or form new chemical bonds. We can't lose or gain mass. Okay, that's some of our rules. All right, so here's an example of us writing out an actual chemical reaction. So if we look here, we're putting heat energy in, and we have potassium and chlorine and oxygen all in one compound linked together as a liquid. And through a reaction, we produce, where this little arrow is at, we get new things. So notice how the bonds here were broken, and we made potassium and chlorine stay together, but the oxygen separated apart. So we see the breaking there. Down here, same idea, where we had glucose with oxygen, and they break and reform new compounds. So when we start with one type of compound and we form new stuff, and there's an energy change, that's a chemical reaction. Okay? So we have to learn how to write them. So first thing we want to do is all of the starting things, like whatever we put in, maybe call those our ingredients. We put them on the left-hand side of our document. Okay, we follow that with an arrow that tells us that we're going to make something. All right, it's kind of like an equal sign in math. And then anything that we produce or we make from this are written on the right of that arrow. Okay, if we have more than one substance, we use a plus sign to separate them. So think almost like a math equation, where anything you start with plus anything else you start with will equal things that you make plus other things that you make. Okay, you may not have plus signs because sometimes there's only one reactant or one product, but you will always have an arrow to separate your reactant side to your product side, or your starting side to your ending side. Okay, so here's an idea of how it works. We call this a skeleton equation because all we have written down are very basic things. They're just the skeleton of what we have. Okay, we have our arrow that separates our reactants from our products. We have two products that the plus sign is separating here, water plus oxygen, okay? And then we have our one reactant, our one product, and our second product is what we have, okay? So this is only the bare bones information. Now we can add more than this, but these symbols are our key things. The product, what we are going to produce, and then any separators, okay? So we have additional symbols. Obviously the plus sign we've already talked about, that separates substances. The arrow separates reactants and products. If we have a reaction that can reverse on itself, which does happen, we have reversible reactions. Reversible reactions can happen, and we use a double arrow for that. Okay? If we have a catalyst, and a catalyst is something that makes our reaction happen faster. Okay? If they're not a reactant, they're not a product, we actually just write them above the arrow. So X can be any catalyst. It doesn't have to be an X, it can be any symbol compound we want to put in there. Okay, X is just a placeholder. If we know about heat or energy, we use the Greek letter delta, which looks like a triangle to us. We can put in the states of matter. We can put in solid as a lowercase s. We can put in L for a lowercase l as a liquid, and we can use G for a gas. There's also that state of matter that's kind of unique, where if we dissolve a solid into water, we get what's called aqueous. So when we dissolve things in water, we have a special state of matter that we call aqueous or in solution. Okay? So these symbols can also be added to our equations. So when we add those to our equations, we start seeing some more complexity. We see that here we have aqueous and liquid and gas. They're written as subscripts with parentheses around them to tell us that this thing, the H2O2, the hydrogen peroxide, was in solution. That water was made as a liquid and oxygen was made as a gas. So it gives us more information about that chemistry. We see that heat was produced here, so we put it on the product side. So if this thing got hot and it actually released energy to us, that would be put over here. Now, if this reaction didn't release energy but had to absorb it or take it in, we would have put that triangle on this side instead. Okay, so this side would be if we're absorbing energy, this side would be producing energy. And then finally, we have a catalyst here. So this is potassium iodide, or Ki. This happens to be the catalyst that speeds up this particular reaction. Okay, so we want to practice some of these to do this. So that was kind of in class. We did a lot of practice. So here we have heating by adding heat energy, aluminum oxide Solid reacts with. So reacts with is kind of a key thing to tell us there's a plus sign there. Carbon dioxide gas to make, which tells us how we're going to produce solid aluminum carbonate. So we added heat energy. We have the aluminum oxide reacts with carbon dioxide gas to make, that's our arrow in red, the aluminum carbonate solid. Okay, so we're taking this sentence and rewriting it as a formula instead. Okay, let's do another one. Aqueous lead nitrate, so that would be the first thing we write. In solution, so that tells us it's going to be AQ. Reacts with, so we see the reacts with, so that will be a plus sign. Solid calcium, okay, so we put the calcium. To form, that would be our arrow. Aqueous calcium nitrate, so calcium nitrate, or this formula in solution because it's aqueous, and lead solid, so lead would be our solid. This reaction also produces heat, so now heat would be on the end. So let's see it again. We have our lead nitrate in solution, reacts with calcium solid to form calcium nitrate in solution and lead solid. This reaction is producing heat. Okay, so we take this huge big sentence, which is a lot to write, and as chemists we can write something really quick and simple that tells us all the same information. That's the value of writing equations, is that we can do something very quickly with symbols and not have to write huge long sentences, which we don't like to do because we're lazy in chemists. Okay, and our last one here, we have hydrogen peroxide aqueous plus our catalyst Ki, making water as a liquid and making oxygen as a gas. Okay, now we have additional practice that we did in class on a worksheet that you should be turning in as part of your assignments. When we have these reactions, we have to make sure that we do not gain anything or lose anything in terms of mass, okay? It's one of the fundamental laws of our universe is that the mass has to be conserved, okay? The actual wording is this: in any chemical or physical process, mass cannot be lost or gained. It must be conserved or stay the same, okay? So if you ever think you lose mass, okay, you might be thinking like, wait a minute, Mr. Dirksen, like, there's a bonfire and I carry down bundles and bundles of wood and it's super heavy, and then we burn the wood all night long, and that's chemistry. You've told us that burning is chemistry, and at the end we have this little like maybe this little handful of ashes that's left over, and there's no way that they weigh the same. And I'd be like, you're absolutely right, they don't. But what you don't see happening is as that bonfire was working, you were making a lot of gas, and it was just floating away, and you didn't even know that. Okay, so if anytime you think that you are going to lose mass, what really is happening is that you are somehow making something that's a gas, that's clear usually, and it just floats away into our environment. Okay, this is where we have some issues with like burning fossil fuels and those kind of things, where people didn't really understand that burning all these fuels was producing carbon dioxide and bad gases that ended up having some ozone effects and actually hurting our environment, causing global warming. Okay, so really we always have to have the total mass before has to equal the total mass after. Okay, so here we have sodium bicarbonate, baking soda. Here we have vinegar or acetic acid, and when we react those two together, they have to have the exact same mass on both sides of this reaction. Okay, now because of that, we can actually keep track of this idea of where the mass is. Okay, and that's where the chemistry comes in and the learning comes in. Okay, to do that, we have to be able to count how many atoms of each substance we have on either side of the reaction. Okay, so everything on this hand side, on the left hand side of the arrow, has to be the same as everything on the right hand side. Okay, and those chemical equations are going to let us help count it. So if we take a look at sodium, I see one Na or one sodium on this side. I see one sodium on this side. So we have one sodium of that side of that. Okay. If we take a look at our hydrogen, I see one hydrogen plus one more here and three more here. So I see 1, 2, 3, 4, 5 of those. Remember, this little subscript tells us there's 3 of these hydrogens. So I see a total of 5 hydrogens here. I see the 1 here and the 4 here. Okay. Carbons, I see 1 here and I see 2 more here. So I see a total of 3. Oxygens, I see 3 here and 2 here. So I see a total of 5. Okay. Come over here and we count. We have our 1 sodium. Hydrogen, I see 3 here plus 2 more here for 5. Carbons, I see 1 here. I see 2 more here for 3. And oxygen, I see 2 here plus 2 more for 4 plus 1 more for 5. Okay. Notice how the amounts 1, 5, 3, 5, 1, 5, 3, 5 are the same. So that has to be true for this chemistry to work. Otherwise, this law in our universal world is broken, and that's not okay because we can't break laws in chemistry and physics. Okay? So we have to be able to count them. Now, here's your rules for counting. We have two different numbers we have to look at. One's called a coefficient. That's the normal size number in front of the substance. That's like the 2 here, the 3 here, the 6 here, the 4 here. Those are our coefficients, we call those, okay? They tell me how many of the entire substance we have. So this 2 says I have 2 H2Os. I have 3 Al2SO4 3s. I have, oh wait, there's nothing here. Oh, if there's no coefficient, that's a 1, okay? So that means that there's 1 magnesium here, there's 2 oxygens, and 2 hydrogens here, okay? So the coefficient basically is like everything that follows it, it has 3 of those, okay? Now the subscript, that's the smaller number written behind an element. So like here we have a S for sulfur, and we have a subscript behind it. So that means there's 8 sulfurs. Here I have 2 hydrogens. There's no number here, so remember that tells us there's 1 oxygen, okay? Here I have 8 hydrogens, and I have 2 carbons. These are a little bit trickier because we have these parentheses. Remember in our last unit, if we had a 3 outside the parentheses, it meant it accounted for both of the things. So I have a sulfur, and I have 3 of those. Now I have 4 oxygens, and I have 3 sets of that. So I have 4 times 3 for 12 of those, okay? So that's how you account that, okay? Again, if there's no subscript, that's a 1. All right. So let's do some counting, okay? Over here, I see 2 times 2 for my hydrogens, so I have a total of 4 hydrogens. I see 2 times 1, so I have a total of 2 oxygens, okay? Here I have 1 magnesium. Then I have 1 out front, so I have 1 times the oxygen times the 2. So I have 1 times 1 oxygen as a subscript times 2 subscripts. Hydrogen's the same, okay? Let's get to a complex one, okay? So for the aluminum, I have 3, I multiply it by the subscript. So I have 3 sets, and aluminum is sets of 2, so it's 2 times 3 for 6. Here's where it gets tough. I have 3 for the sulfur, because this multiplies by everything. I have 3 for the sulfur, times 1, there's a 1 here, we don't show it. So 3 times 1 times 3. So that would be 9, okay? For the oxygen, I have 3 times 4 times 3. So there's actually 36 oxygens in this compound because we have 4 of them inside of here. Triple that for 12, triple it again for 36, okay? Following that same pattern, we have our barium chloride count, our gallium nitrate count, and our zinc phosphide count. If you want to pause this to see how those all work out, you can. Now, when we count these in equations, you have to break it apart. So I usually do a reactant side and a product side, and then I just go ahead and I list all the elements I have. So I have sodium, I have sulfur, I have barium, I have chlorine, and I can just go ahead and count how many I have. My 2 sodiums, my 1 sulfur, my 1 barium, and my 2 chlorines. I have 2, a 1, 1, and 2 again. They should be the same for now, okay? Later on, we'll have to figure out what goes on. Same thing here, where I have my 2 aluminums. My oxygen's a little bit more complex because I have 1 out front times 3, so that gave me 3, plus I have 3 times 2, so 3 plus 3 times 2 is a total of 9, because this is 6 plus 3 is 9, okay? Carbons is 3 here, and then 2. Here my oxygens are just 3 times 3 for 9, and my carbons are 3. And then for my lead nitrate with calcium 1, again, we see those adding up, okay? Again, pause these if you need more time with that. We all obviously have some practice that we'll be doing in class that works with this also, so you can do that practice as one of our assignments. Now, what happens if we don't have equal numbers, okay? We actually have to go through this process called balancing a reaction, okay? So we look down here, I have 2 carbons, carbon times 2, but over here I only have 1 carbon. Okay, so they're not equal to each other, so that would break the law of conservation of mass. So it's going to be our job to put blanks in out front and actually put the right coefficients in to actually make this balance, okay, to satisfy that law of conservation of mass, okay? So if I have 2 carbons here, I'm going to want to put a 2 here to make 2 carbons on this side too, okay? So we're going to use our counting skills and this idea of conservation of mass to make it work. I always say play a game, okay? So let's do a little game board. And let's first write down how many of everything I had to start. So I have 2 carbons on this side. I have 6 hydrogens. I have 5 and 1 over here for 6. I have 1 oxygen plus 2 more for 3 on this side. On this side, I have 1, 2, and 3. So if we look, my oxygens are the same. That's good. My carbons are not the same. My hydrogens are not the same. So I need to fix it, all right? So what I'm going to do is I'm going to fix the carbon first. So I have 2 carbons on this side, 1 on this side. So I'm going to put a coefficient of a 2 here. So by putting a 2 here, what happens is that 2 multiplies to the carbon and it multiplies to the oxygen. So I end up having not 1 carbon now, but 2 carbons. But it also doubles my oxygen. So this 2 is no longer valid. So that's not true anymore. So instead of having 2 there, I have 4. 2 times 2 is 4, plus my 1 for 5 total oxygens. Sometimes when you balance equations, fix one thing, you break something else. Okay? That's okay. We'll fix it. All right? So next thing I'm going to do is I'm going to try to fix my hydrogens. All right? So I have 6. I have 2. If I put a 3 here, 3 times 2 will give me 6 hydrogens. Fixes that. And then my 1 is no longer valid. So that is now not true. So now I have 3 times 1. So instead, I have my 4 oxygens here plus my 3 more. I have 7 oxygens on this side. Okay? That's okay, though, because now I have 1 oxygen here plus something times 2 to give me 7. Okay? So I need to get 7 of these. So 1 plus 6 gives me 7. So if I make this a 3, I have 1 plus 3 times 2. So that would end up being 7, okay? So that's kind of the thought process we go through when we balance equations is we fix things, and I like to keep track of it here in my little game board as we do it, okay? And then, of course, any blanks you have here, you don't have to put a 1 out front, but you're always welcome to put a 1 there too, okay? So here's some more practice for this. We're going to go kind of fast through it because this is what we did in class to do this practice. So things for help you out for tips or tricks. If a polyatomic ion is present, okay, so like right down here we have NO3 as a polyatomic ion, and we have an NO3 here again. If you see that, don't separate them. Keep them together. So don't make them nitrogen and oxygen. Make it all one nitrate, NO3. Do your most complex thing first. That's always the best rule. Save any element that's alone for last. And try to do oxygen towards the end too, okay? So like down here, I would do copper last or silver last because they are alone. Here, I have hydrogen or oxygen, so I have a lot of alone things. So I would probably do the hydrogen first and then do the oxygen last for this one, okay? So if we balance these again, we start off with counting them and then setting them up. And then same thing over here. We count them and set them up and put the numbers as we need, okay? Here's even more practice for us. So I'm just going to fill these in so you have them. So you have those in your notes. We'll go back to that one for you. So you have these for your notes, and that shows you how we can balance those. Okay. There is additional practice in your notes also to practice this more. Thank you.